This is Rosen, Discrete Mathematics and its Applications. We're in section 8.2 where we will learn how to solve linear recurrence relations. In this video, we'll be addressing linear homogeneous recurrence relations with constant coefficients. And that is a linear recurrence relation where a sub n is expressed in terms of the k prior terms, and the coefficients are all constant. It's linear because the right-hand side is the sum of previous terms multiplied by a function of n, and in our case, they're all constant. It's homogeneous because no terms other than prior values for the sequence are in it. And degree k because it's expressed in terms of the previous k terms, or reaches back to the kth prior term. And if you have a recurrence relation of degree k, then the sequence is uniquely determined by k initial conditions. So if we start at a0, we need to go up through a k minus 1 and establish those values to have a unique solution to the recurrence relation. Here's a few examples. This is a linear homogeneous recurrence relation of degree 1, only reaching back from n to n minus 1. That would be the interest relationship in terms of return on a deposit in a bank. Here we have the Fibonacci recurrence relation. It is a linear homogeneous recurrence relation of degree 2, reaches back to the 2 terms prior. This recurrence relation is not linear because of this squared term in the a sub n minus 2. This one's not homogeneous because we have a term that is not related to a prior term in the sequence. And here we have a recurrence relation with a non-constant coefficient. So we will not address these types in our section. All right, if we want to solve a linear homogeneous recurrence relation, we're going to look for solutions. A sub n is equal to r to the n power, where a sub n equals r to the n is a solution to the recurrence relation if and only if where we substitute r. Here we get r to the n, here we get r to the n minus 1, here we get r to the n minus 2. So it has to satisfy this equation. So I just substitute r sub n, or r to the n here for a sub n, r to the n minus 1 for a sub n minus 1, and so forth. Now if I take all my terms to the left side of the equation and I divide by r to the n minus k, which I can do because r is non-zero, I get what's called the characteristic equation, which is r to the k minus, or everything on the right-hand side up there, minus ck is equal to 0, and a to the n equals r to the n if and only if r is a solution or a root of the characteristic equation, and we call these the characteristic roots for my recurrence relation. And they'll be the basis for establishing a closed form solution. Here's our first theorem. We're going to talk about recurrence relations of degree 2. And here's my characteristic equation for this recurrence relation right here. And if it has distinct roots, R1 and R2, then a sub n sequence is a solution if and only if, this is a 1 there, A sub n equals alpha 1 r1 to the n plus alpha 2 r2 to the n. Okay, so let's see if we can apply this theorem. We have a linear homogeneous recurrence relation of degree 2. We have two initial conditions. So my characteristic equation will be a polynomial of degree 2 since it's 2-degree recurrence relation. Be 1, excuse me, that's a 1 there and a 2 there, so we're going to get a -1 and a -2 here for my coefficients. And if I need to factor that, I get the roots are 2 and -1. So I can write down the form of my solution as alpha 1 times 2 to the n plus alpha 2 times -1 to the n. And now we will solve for the alpha 1 and alpha 2 using the initial conditions. A0 is equal to 2, and since the index is 0, the n's are all 0, and I get values of 1 for their result, so alpha 1 plus alpha 2 is A0. A1 is equal to 7, that's given, and then it's also equal to alpha 1 2 to the 1 and alpha 2 -1 to the 1. Now I have two equations and two unknowns. I could solve for alpha 1, substitute the other equation, and then find alpha 2 and substitute back to get alpha 1. In the end, we get alpha 1 equals 3 and alpha 2 equals -1. Did it work? Let's see. Let's solve for A2. A2 using our recurrence relation is A1 plus 2A0 is equal to 7 plus 2 times 2 equals 11. Let's try this. Let's try our solution, which is A sub n is equal to 3 times 2 to the n minus a -1 to the n. So A sub 2 equals 3 times 2 squared minus -1 squared equals 11. So it works. All right, let's look at the theorem 2 has to do with when the characteristic roots are equal. We have a multiplicity of them. And I'm going to skip through this real quick. You can look at these slides on your own. Here we go. Theorem 2, solution when there's a repeated root. So if I have a characteristic, my recurrence relation is given here with this characteristic relation here. But in this case, we're going to have a single repeated root, R0. In that case, A sub n is a solution if and only if it obeys this form, alpha 1 r0 to the n, and alpha 2 times n r0 to the n. So let's apply this theorem to a recurrence relation. Here I have a recurrence relation of degree 2. Here's my initial conditions. Take a look at the characteristic equation. And you'll see that if we try to find the root for that, we get, that's r minus 3 squared equals 0. So we get r equal 3 with multiplicity 2. So I can write down the solution. It's A sub n is equal to alpha 1 3 to the n plus alpha 2 n 3 to the n. And I've got to solve for my alpha 1 and alpha 2 using the initial conditions. At A0, that second term goes to 0, so I just got the first term. 3 to the 0 is 1, so 1 equals alpha 1. Alpha 1 is 6, and then my exponents are 3 to the 1, 3 to the 1, and this also has times 1. So alpha 1 times 3 plus alpha 2 times 3 is 6. Alpha 1 is 1. So alpha 2 will have to be 1, so to get 3 plus 3 is 6. And so my solution is 3 to the n plus n 3 to the n. Let's check it. Using my recurrence relation, a2 is equal to 6 times 6 minus 9 times 1 equals 27. And for this one, a2 equals 3 squared plus 2 times 3 squared. That's 3 times 3 squared. That equals 27. And so that's application of theorem 1 and theorem 2. There are generalizations of these theorems that you need to look at in the text as well.